All right. Hey everyone. I'm Jay, and I'm a full stack data scientist at VIACOM CBS Streaming. Basically, I build data products powered by machine learning in the world of SpongeBob SquarePants and Star Trek. I would like to thank Data Science Alan for inviting me in. Um, I don't work for a traditional data science company, as you would have already known. Um, Yeah, so if you don't know, Viacom CBS is a global media and entertainment company that creates premium content and experiences for audiences in 180 plus countries with brands such as CBS, Paramount, Comedy Central, MTV, Showtime, Nickelodeon, and Colors, with the latest edition of Paramount Plus. My team does all things data for most of the digital and streaming products, from ingestion to modeling to building data products, mostly focusing on our streaming service, Paramount Plus. So today I'm going to talk about data science in production, bringing machine learning models to life. If you are a software engineer turned into a data scientist, you would probably know some of these. But for someone who is at school or is a straight up data scientist, they would be mostly working out of Jupyter notebooks. It's been why talk about it? It's been about an year since I wrote a blog on full stack data science, the next generation of data scientist cohort, which got hundreds of shares on social media along with mentions from AI communities and companies from all over the world. Also, I delivered a talk on that at few conferences, including Data Science Alliance, focused on media and entertainment. After that, I understood the need of tools and techniques which no one teaches in schools or universities, even if you are a data science major or a computer science major, which is creating a huge talent gap in the industry. But I feel day by day, they're getting incorporated into schools' courses. So you would ask how to bring machine learning models to life. And I would say it's not that difficult. Let's dive into it. APIs, short for Application Programming Interfaces, user interfaces, and data and machine learning pipelines. Don't worry, we'll dive into each of these. So API. API is an application programming interface, which basically means that it is a computing interface that helps you interact with multiple software intermediaries. Uh, when you hear about APIs, you also would have heard about a word called REST. What is REST? REST is representational state transfer, and it is a software architecture style. Let me just show you in a simple diagram what I'm talking about. So client can interact with your system, in our case, to get predictions by using our built models. And they don't need to have any of the libraries or models that we built. It's just become easier to expose your models internally or externally, even for your side projects. So we can build APIs that will serve our machine learning model, and we can do all that in Flask. Flask is, again, a web framework for Python. You must have heard about two substantial names in the industry, which is Flask and Django. Flask and Django are both amazing web frameworks for Python. But when it comes to building APIs, Flask is super fast due to its less complicated and minimal design. First step always would be to set up your own project environment that you can isolate your project libraries and their versions from interacting with the local Python environment. This is also a good practice when you're going to ship your code into production. There are two ways in which you can set up your Python environment for your project specifically, either using virtual environment or Conda. So this is an example code of like creating your virtual environment. So for this example, we are going to go ahead with a project, like an example project. Our main aim is to package and deploy our built machine learning model in the form of an API. So we'll take an example of a Kaggle starter dataset, which is Titanic, and a basic logistic regression model with feature engineering. So if you want to know how I built this basic model, all the code will be available on my GitHub. We can use the pickle library to save the model. Your model, in turn, is a Python object with all the equations and hyperparameters in place, which can be serialized and converted into a byte stream with pickle. We can now move on to build a Flask API with best practices. So code management and best practices. So what best practices? Like how to create a clean code that can be shipped to production and easy to debug if any issues occur. We can create like helper function Python modules, which has all the pre-processing functions we'll need. Again, this is the same pre-processing code that you wrote while building the model, but we'll create functions out of it to be reused anywhere else. Now, we should also not hard code the variables or names that we'll be using in our final API. So we can create separate Python files like configs.py, which will basically store all our variables for security purposes. We can then import all the libraries in the code, as well as all the helper functions and configs with variables. To start with, this is how a simple Flask type hello world looks like. In the Flask world, it's called a route. Routes are generally the URLs which will be supported by functions. So basically to build a prediction route in our new route with like added predictions, what happens is if someone sends a GET request to this URL of your Flask application along with raw data in form of JSON, we will pre-process the data the same way we did for creating the model, get predictions, and send back the prediction results. As you see in the code, request.getJSON will basically give us the JSON data that was sent with the GET request. We convert that data into a data frame, use our helper function preprocess to preprocess the data frame, use the model name and column names from the config file to basically load the model with pickle and make predictions on the sliced data frame. So after making the predictions, we'll create a response dictionary that contains predictions and prediction label metadata, and finally convert that to JSON using JSONify and return the JSON back. So I generally use Heroku for deploying my side projects as it's less hassle. Heroku is a cloud platform that helps you deploy backend applications on their cloud. This is how you can test the API that you created, basically getting the input data and sending a GET request to the URL of your deployed project. And in return, you'll get the predictions. And this dummy project is live right now, and you can test it out. Even I'm going to show you how this works. So if you go to ML API, just the hello world task that we wrote, you can see the response coming here. But if you send a GET request, then you'll get the predictions. So now we're going to talk about user interfaces, how you could quickly build interactive web applications, which uses machine learning, and how to deploy those applications into the cloud. You can go for any framework, but if you don't have much of web development experience, I would go with Dash. So Dash is an open source web framework built by Plotly, especially designed for data science and AI applications. Full stack applications that would typically require a front end, a back end, and a DevOps team can be built and deployed in hours by data scientists with Dash. Yes, you can do everything in Python, which is beautiful. Dash is built on top of Flask, Plotly.js, React, and React.js. But we can write most of the code in Python with some embedded HTML and CSS elements. Let's take an example of game of cricket. We will be building a predictive model for the game of cricket, and We'll be using the Kaggle dataset, which is on Indian Premier League. Indian Premier League clocks a reach of 462 million, watch time of 338 billion minutes on TV. So this is the layout of the web app that we want to design, and it's pretty straightforward in terms of UI design. I would not say it's the best, but it should do the job. We have to define each and every element in the UI in our dash layout. We have to specify IDs and styling of each element to be able to control and fetch data from them and process it in the backend. This is how you define UI for a Dash app with simple HTML elements. As you can see, like we have defined all the elements that you saw before in the web app UI. So now we want to make it completely dynamic, such that when random forest or neural networks are selected, then and only then we get an option to tweak the model parameters and don't see them otherwise. So we'll be using callbacks to change the UI dynamically when drop-down option changes. So as you can see, these 6 callbacks will make visibility of parameter setting completely dynamic. And it's easy because of just some conditional statements to check values and set properties. Likewise, when there is a change in the drop downs for algorithms. So now we'll do the fun part, which is making the dynamic ML component, which will basically update the predictions quickly when we update the features or model parameters. We'll again be using dash callbacks to update the prediction components of the page when there is a change in feature or parameter components. So again, we can deploy the Dash app on Heroku as well, or any of the cloud that you are familiar with. This as well is live, and you can test it out on iplpredict.herokuapp.com. And if you want to see it, I'm just gonna show it. So by default, linear regression and logistic regression are selected in like 3 types of prediction models that we built. So if I want to go with, suppose, random forest, then it would basically pop up the parameters that we could tweak. So suppose if we do like a number of estimators as 50, the scores dynamically changed. And these are all the features that goes into the model. So suppose runs, so it's a game of like 20 overs. So let's say a team makes 90 runs at 15 overs, has a predicted score of 135. But how about if the team makes 100, or suppose, let's say, 110 runs? The predicted score went up to 162. Similarly, we can do that for win prediction. So suppose if we select a neural network and runs at 20 overs are like 120 for the first team, if we change that to 150, then the win prediction for the first team would be 46.92%. So this was a good example of how we can expose our built machine learning models via an UI. So let's now talk about machine learning and data pipelines. Did I just say pipelines? Yes. The first framework that would come to my mind would be Apache Airflow. So Apache Airflow is an open source workflow management platform, thanks to the folks at Airbnb who open sourced this project. I love Airflow. It helps you automate data pipelines and machine learning pipelines, and it is widely used in the industry. You can do ingestion, perform ETL, perform ML tasks, automate things you do daily. It can be easily integrated with Apache Spark as well for doing distributed processing. That's how Apache Airflow UI looks like. All these lines that you see are each of them is a DAG. So in Airflow, DAG is a collection of all the tasks you want to run, organized in a way that reflects their relationships and dependencies. A DAG is defined in a Python script, which represents the DAG's structure, tasks, and their dependencies as a code. So this is an example DAG. So it has start, fetch tweets, dump tweets, and end. So we can let's talk about connections. So connections is an important part of Airflow. We can make the use of connections in which you can store JSONs with some of the variable information you don't want to expose out, as well as it is specific to a DAG. So we can get all the config variables used in the code from this connection. This is how a connection looks like and how you define it in the Airflow UI. Everything can be done via the UI, which is pretty cool. Variables. So we define variables in the script, but Airflow has its own set of feature called variables. So we'll use variables of Airflow now to store information which can be shared by multiple DAGs, such as account token for some of the APIs, like Twitter's API in our case. This is how you get to the variables from the UI, and you can create new variables. It's XForms. So we'll be using XForms for communication. Once the first step will store the tweets information in a list, then it will have to push this information in an XCOM variable, which can be retrieved in another task. So XForms are used when communication is needed between downstream tasks. So this is the sample code for both of the functions that you just saw on the DAG, which is basically to fetch tweets and then dump tweets. So the first function here, you can see it basically like fetches tweets from Twitter using the API, and then basically pushes them into an XCOM variable. And then in the later function, dump tweets, which is again another task, it basically fetches from the XCOM, and then it basically dumps into files. So, and later on, like the functions you have written, you can define the DAG task and use those functions out. So you can see start operator, end operator, fetch tweets task, dump tweets task, and then you line them up, defining the flow of the Airflow DAG. So basically start operator to fetch tweets, dump tweets, and end operator. You can really write really complex tasks in Airflow, which is amazing. So while I was in my master's, I was also a research assistant at Center for Computational and Data Science at Syracuse University. I was working on a computational journalism project. The tech stack they used before was something like Python, cron jobs running on the servers that collect data, and other cron jobs which tag data with machine learning models. The project is funded by the prestigious Knight Foundation. It's on analyzing presidential and gubernatorial elections in the states on social media in terms of content. In the latest iteration, we focused on ads run on Facebook and Instagram. So if you go to illuminating.ischool.syr.edu, you can access the web app we built. You can check the About section to see how we leverage BERT model to classify content in ads into various categories to understand the context of political campaigns. This is a really cool project which received a lot of traction during the US elections last year. So the data that you see here updated every 4 hours, making this project a behemoth during the elections. And in the backend, we used Apache Airflow on our servers to collect data every 4 hours, apply machine learning models to it, and push into our MongoDB instances on other servers, which will fuel the web app. So basically, for all the classification tasks that you would see on the UI, or all the classifications of all the campaigns run, we use the state-of-the-art language model BERT, and all this We can quickly go over the live web app, which we have. If you go to illuminating.ischool.syr.edu, and then you go to like campaigns, there would be like 2020 presidential campaign ads, and you can see basically everything. So suppose if I want to see the classification, like what kind of messages they posted as ads, you can see all the classification of what kind of messages they posted: age, location, message tone, civil, uncivil, message topic, what they talked about. Everything is completely automated and built in a system which in the backend uses Apache Airflow to collect data real time, almost real time, not real time, but almost real time. Um, yes. So yeah, that was pretty much it. Thanks for tuning in. Feel free to connect on LinkedIn, and you can also check out my blogs on Medium, which has tutorials on all the three things that I talked about today: APIs, user interfaces, and uh, pipelines. Thank you.